All right, so you might want to pause the video and go ahead and write these 4 examples in your foldable. Um, and now we're going to talk about the definition of a vertical asymptote. I gave you the layman's terms on the back for your words worth knowing, but this is the mathematically precise definition. So if f of x, your function, approaches infinity or negative infinity as x approaches c from the right or the left, then the line x equals c is a vertical asymptote of the graph of f. That makes sense to me. I don't know if it does to you, but I want to get you used to seeing that language. So basically, this is just saying that if your function has an infinite limit at a point C, then x equals C is a vertical asymptote. If you have infinite limits, then you're having an asymptote of some kind. That's basically what this is saying. So let's talk about how to actually find vertical asymptotes. And like I said, you learned this in Algebra 2, so it may come back very quickly. We call these in Algebra 2 excluded values. So wherever you have an excluded value, you're typically going to have a vertical asymptote. And we'll talk about sometimes you don't have a vertical asymptote with example D. So with example A, to find the vertical asymptote, we want to find the excluded value. We want to find where does this function mess up? Well, we have a fraction and we can't have a 0 in the denominator, so that's probably what we're going to look at. So we're going to say 2 times the quantity x plus 1 does not equal 0, because that's the value that we can't have in our graph. And so now we're going to solve this little equation. I'm going to divide by 2 on both sides, and I end up getting x plus 1 cannot equal 0. And then I subtract 1 from both sides, and I get x cannot equal negative 1. So what this means is that we have a vertical asymptote at x equals negative 1. And we've just found the asymptote. And then we could attempt to determine the limit from the left and the right of x equals negative 1, but you're going to want a graphing calculator to do that. Now let's look at B. So with B, we've got, again, a fraction. So we're going to need to take that denominator and set it not equal to 0. Now, some of you are thinking about this in different ways. We could factor using DOPS, difference of perfect squares, and solve from there. Or we could use a square root property. We can move the 1 over to the right side and then do the square root of x on both sides. Now this only works for x squared. It's called the square root property. So there's no such thing as a cube root or fourth root or any of those. There's just a square root property. So this is a little shortcut you can do instead of factoring. But anyways, so I'm going to square root both sides, and when I square root the 1, I just get 1. But when you use the square root property, you have to do plus or minus. So that's the only bad thing about using the square root property, is a lot of people forget to do that. So plus or minus for square root property. A lot of people forget that. So that's why I typically advise you just to use DOPS. But anyways, you can see here that we actually have 2 values that x cannot be. And if you don't trust that, you can plug them in to the denominator and you'll see it turns into 0. So this just means we have 2 vertical asymptotes. So we have vertical asymptotes at x equals 1 and at x equals negative 1. So then we could determine some infinite limits around both of those c values. Now let's take a look at this one. Right away, I don't really see anything that could cause a vertical asymptote. But we know that cotangent has asymptotes. We know that if we graphed it, that it has some issues. Let me type this in. 1 divided by tangent of x. So there's my function. Remember, there's no cotangent button in your calculator, so you have to do 1 over. And when I graph it, holy cow. Okay, graphing calculators have a hard time with cotangent. I can hit zoom trig. I didn't hit zoom trig. Hold on. There we go. So that looks a little prettier, but you can see there's asymptotes. So how do we determine that algebraically? That is the question. Well, remember that cotangent is one of our quotient identities. So we can rewrite this as cosine of x over sine of x. It's a quotient. It has a denominator. Oh, okay. So when sine of x equals 0, that's when we have our vertical asymptotes. So we take that denominator, we set it equal to 0, and we have to kind of remember, well, where does our sine function equal 0? It's been a while, so let's draw our sine function, and you can see that it equals 0 here and here. And of course it keeps repeating on towards infinity, but we're just going to write the first two answers. So we'll say that x cannot equal 0 or pi. And then I'm going to put comma dot 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 because I'm lazy. Okay, so vertical asymptotes are going to appear at 0, pi, and continue that pattern on towards infinity. So 2 pi, 3 pi, so on and so forth. So I need to write my vertical asymptotes are x equals 0, pi, dot, dot, dot. Why am I writing this twice every time? Because this is the excluded value notation, saying that it can't equal this. And to say something's a vertical asymptote, you have to write it as a line. And that's why we write x equals. All right, so last example. This is a tricky one. Okay, this is where not every excluded value turns out to be a vertical asymptote. So we could just take our denominator, set it equal to 0, solve it, and we'd get our answer, but it wouldn't be exactly precise. Notice that the top here can also be factored. So we want to simplify this function before we find the vertical asymptotes. So I'm going to simplify it over here because there's not a whole lot of room. I'm going to factor the top. The top is a trinomial, 3 terms, where a equals 1. So I'm going to look at the factors of -8 that add up to 2. So factors of -8 that add up to 2 are going to be 4 and -2. So I write those in here, write down my x's, and I've factored the top. Now I need to factor the denominator. So up here we used the square root property, but this time we're going to use dops. So I'm going to write my 2 parentheses. The square root of x squared is x and x. 1 plus, 1 minus, and the square root of 4 is 2. Okay, so now you see that there's a similar factor on top and bottom that can be canceled. Okay, so this excluded value actually isn't a vertical asymptote. That is what we call a removable discontinuity. And if you don't remember what that is, you can look back a couple lessons. We talked about that. So that's the difference between these two. Since that one could be canceled, that's a removable discontinuity. Whereas this factor, x plus 2, is going to give us a vertical asymptote. So our VA is x equals -2. So excluded value notation, line notation. And we do not include this excluded value because that's a removable discontinuity.